So, as I said previously, we want now to go into the models of radiation action, at least the classical models of radiation action that are mostly used also in radiotherapy when you use ions. So generally, let's say all models assume that cell inactivation is a multi-step process. This is clear. That the absorption of energy in some critical target is crucial. Of course, we know that this critical target is the DNA, but we have seen that the scale can also be micrometric, not necessarily nanometric. Deposition of energy like ionization or excitation can yield to a molecular lesion. This we have seen in the radiation chemistry lecture. And the expression of such lesion may cause to the loss of cell's ability to carry out normal cell division. So this word expression of the lesion is crucial. You know, this means, you know, unrepaired, or can mean misrepaired breaks, or other process we have seen that can lead to inhibition of autophagy rather than apoptosis, rather than necrosis, rather than mitotic cell death. This is a little bit a historical chart, you see, from the discovery of X-rays to the first models for radiation biology. The target theory already introduced in the 20s, but then perfected by Douglas Lee, that is one of the greatest genius in the field of radiation biology, in his book in 1946. And later, you see refinement of the Lee model by Elkind and Whitmore. Microdosimetry that we have seen already in the physics part. So the linear quadratic model by Keller and Rossi, that as we have seen is apparently able to explain most of the things that we see, because clearly gives you an idea of how you can produce a linear quadratic dose response for both chromosomal aberrations and cell killing, and also explains a lot of things we will see, like the RBE, the dependence on the dose rate, and so on and so forth. So it's a pretty powerful model that has been perfected a lot. There are then other models, for example, the lethal, potentially lethal model and the repair-misrepair model. These two models are very similar. They were both coming from Berkeley. The saturable repair model by Oxford, Dudley Goodhead at Oxford. And then more modern, you see, this is the era of the linear quadratic models. These more modern approaches are more based on analysis of repair kinetics, so molecular studies. These modern approaches are still, I have to say, still unable to provide models that are easy to use in radiotherapy, for example. So we are still using these models, or we will see for heavy ions, amorphous tract models. But the linear quadratic model is still the basis for radiotherapy. As I told you, the theory of radiation action is really greatly explained by Douglas Lee in his book in 1946, that, by the way, I have in my library, so and I'm very proud of it. It was very difficult to find. So if you want to see it, I can show it. It's amazing. To read this book is amazing, because you will see that how Douglas Lee understood an enormous amount of radiation biology without having the molecular biology knowledge that we have now. So it's really unbelievable. Unfortunately, Douglas Lee died very young. You see, he was only 37 years old. One year after the publication of this book in a car accident. He was professor at the University of Cambridge already, the same college where Newton used to teach. And I really think is one of the greatest genius in the history of radiation biology. Not very well known. I don't think that many of you have ever heard of Douglas Lee, but it's really impressive what he has done. The first simple approach of Douglas Lee to radiation biology is the heat theory or target theory. We will see heat and target theory are actually two faces of the same coin. So in the heat theory, you assume that there is a sensitive target, which is a volume, which has a certain volume V, and you assume that there is this discrete and stochastic energy deposition, which is very clear. Now with microdosimetry, we know very well how stochastic is the energy deposition events. Now, if you have a certain number of hits in V, we call H the number of hits, which are these stochastic energy deposition events in the subvolume V. Let's say that V is the total cell volume, actually not really cell, the total nucleus volume, because already Lee knew that the sensitive target was the nucleus of the cell. And the density of events, D, is actually proportional to the dose, because of course the events are energy deposition, so the density of events will be proportional to the dose. The probability that the cell survive H hits will be this function, H of H. So now if you simply apply Poisson distribution, you will have that the probability, the survival probability to survive to a given number of hits will be H, the sum from H to 0 to K to minus 1, E to minus VD. Now V is the volume and D the density of events, but you can multiply them to have the average number of lethal events, and then the survival will be given simply by these Poisson statistics. Now, if you only need one hit in the target to kill the cell, then of course this equation H for in this particular case S is simply given by E to minus D. And at this point, you know, E to minus VD, V you can traditionally was written as 1 over D37, because when D is 1 over V, the survival is 37%. E to minus 1 is 0.37. But these days is written as 1 over D0. So it's a perfectly linear dose response curve. Now, as we have seen, generally, those response curves are not perfectly linear. They are perfectly linear for viruses, for example. If you irradiate a virus, it's perfectly linear. For very radiosensitive cells, where actually, let's say, a single hit in a way makes sense. A single hit is enough to kill the cell. But it's not perfectly linear when you have mammalian cells. So you change it a little bit. You have the so-called multi-target single hit, where essentially you assume that there is not a single target, but that there are M targets in the cell. If you have M targets in the cell, then the previous equation, let's say this equation here, where essentially you assume that there is only one target, becomes this one. You see, will be 1 minus sum for H from 0 to K minus 1 of this one again, V is 1 over D0, to M. Because of course now if you have M targets, the probability of inactivating this target will be 1 minus this one times 1 minus this factor times 1 minus this M times. So 1 minus the probability of inactivation gives you the survival curve. This is called the multi-target multi-hit. If you have one hit, so K equal to 1, of course this terms again goes to 1, and this is reduced to the simple but very effective multi-target single hit equation that can be written in this way: 1 minus 1 E to minus E to minus D over D0 to M. This is the multi-target single hit equation. How does it look like? It looks quite good. You see, it looks quite good because I say this is a linear single hit, single target. But if you have single hit multi-target, it will be nicely shaped like that. You see, the slope of the curve is 1 over D0, and there is an extrapolation number M. So M comes here is the limit for D going to 0. You see at the extrapolation M here. This dose dq, which is defined here, dq is d0 times logarithm of the M, is the so-called quasi-threshold dose, because you see it's like the problem of the multi-target is that the initial slope, this one, will be always 0, so it is flat here. So you have a quasi-threshold dose. When you start to see the curvature, you can express it in this way. And the final slope, you see in the high dose approximation, this is reduced to this one. So the final slope is 1/d0. So the multi-target single hit looks very good because it gives you a very nice curvature here. And you playing on M, of course, this curvature can go to 0 or can be quite high. There is also one thing which is very important in the multi-target theory, that the final slope is actually exponential. So if you see in the high dose approximation, this is an exponential. So, and this we will see, this is actually what happens. But we will come to this a little bit later. So you see, playing with the parameters, you see, this curve here is m equal 1. M equal 1, of course, is a perfectly linear. Then if you increase m, you see, you increase the curvature. And of course, if you increase d0 will be the final slope. So if you increase d0, the curves shift in this direction. So you can really apparently reproduce with this model a lot of survival curves that we have seen before. But there are, of course, deficiencies. It's a pure physical model, really. I mean, it's very abstract. It's like hitting, let's say, shooting bullets on a target. There is no interaction between lesions that clearly happens in the cell. We have seen the formation of chromosomal exchanges. There is no repair. Repair is not part of this model. If it is single hit, every hit is lethal. What is a hit then? Is an energy deposition of 30 electron volt, or is an energy deposition? You remember in radiation chemistry, we saw that sometimes even stopping electrons at energies of the order of a few electron volt can induce a double-stranded break. So what is a hit? The number of targets m is actually not really realistic. You see, what does it mean? What does it mean that this curve has 3 targets? What is the meaning of 3? Certainly, we don't have 3 chromosomes, for example. I mean, it's just a number, but is not really matching a real molecular component of the cell. Now, there are these 2 questions. Is the straight portion of high dose really straight, and is the initial slope 0? Well, we have now a good answer. At that time, there was a lot of discussion on this point. We know now that the initial slope is certainly not 0. So the problem of the multi-target, also from the mathematical point of view, is that forcing the initial slope to be always 0 is wrong, because in many cases, the initial slope is not 0. You really start with the initial slope. On the other hand, the final slope actually is straight. And the linear quadratic model, if you think to the microdosimetry, alpha d plus beta d squared is not straight, because the beta d squared term means that the curvature increase when you go to very high dose. So you see that the multi-target model is better than the normal linear quadratic model that we have seen, let's say, from microdosimetry at high doses. For many years, people didn't really care much about this story, you know, because they said, okay, well, but normally we always go to relatively low doses. You know, we are always, also in radiotherapy, the single fraction in radiotherapy is 2/4 gray, so it's a low dose. So the linear quadratic model is perfect. But these days, with the radiosurgery, stereotactic body radiation therapy, high-dose brachytherapy, these are things that, if you are interested, we will mention them in the radiation therapy lecture, but there will be a dedicated course in medical physics. If you do medical physics, you will see exactly why. The tendency is to go to very high dose per fraction, so to treat the patients with a very high dose in a single session. So if you do that, now forget about this part of the plot, the biological effective dose. This is still another meeting. But the interesting part is that in this paper, which is relatively recent, you see 2008, it's not 1945, but it's relatively recent, they tried to find the shape for the survival curve, taking into account the which is able to reproduce the data at high doses, because they had the problem that when they were doing radiotherapy with radiosurgery, they were giving 25 gray in one fraction, and the 25 gray, the survival estimated, you see that this curvature here is the linear quadratic. The survival estimated by the linear quadratic was far too low compared to the real survival, due to the fact that the final slope of the survival curves is exponential, it's not continuously bending. So what they have done, a very simple model, if you want. You see, it's a very simple model where the survival is given by the linear quadratic. This is a logarithm, of course, by the linear quadratic equation below a threshold dose called dt, but above the threshold dose is given by this equation, which is exactly the multi-target single hit equation. You see, where d0 is the slope and dq is the quasi-threshold dose. Let's say and this is m, n in this case is called n, but in the target equation is called n. So you see that the multi-target is still used today, interestingly, to complement the linear quadratic equation when you go to very high dose. And in these days, you are going into very high dose. Of course, this is really, how can I say, this is really artificial now, because you decided there is a threshold dose, and the dose above the threshold dose is linear. Where is this threshold dose? I mean, you can only estimate the threshold dose experimentally. So there is now another model, which was also relatively recent, is published in Science Translational Medicine, which is a very good model. Generally, they don't publish mathematical models, but this is a very sophisticated mathematical model, based again on the linear quadratic. But you see, now there is some substantial difference here. There are two factors here. This is not beta d square, but there is a factor g that takes into account, you see here, this is a time-dependent factor, so that takes into account the probability of interaction of the lesions as a function of the time. So if you do that, I mean, if it's a sophisticated, I'm not going into the detail of this model, but you see, for a constant dose rate, I mean, the approximation at low dose rate, this exponential can be written in this way. At high dose rate, this is essentially 0. And so this means, in reality, that at low dose rate, this model becomes similar to the linear quadratic. But at high dose rate, this becomes more linear to the multi-target single hit model. And in fact, you see, it reproduced the data very well also at high dose, becoming more like a multi-target single hit. So this model, which is called universal survival, universal because it covers the full spectrum of doses, and you see, gives you a very good tool. Of course, there are many parameters that you have to estimate, but gives a very good tool to reproduce the survival curves also at high dose. Now, a few notes on other models. For example, if you try getting closer, let's say, to the modern models, this is still old, it's the 80s, but the idea here was to try to use the molecular approach. So you say you have an undamaged state, okay, which is, for example, a DNA which has no lesions. Then this undamaged state can go either toward the lethal lesion, that can be, for example, a complex clustered double-strand break, which is unrepairable, or you can go to a potentially lethal lesions that can be correctly repaired, for example, using homologous recombination, or can be incorrectly repaired, becoming a lethal lesions, for example, alternative non-homologous end joining leading to an asymmetrical chromosomal aberration. So now you only have to write the kinetic equations here. So how you go from a damaged state to a lethal lesions, these are all kinetic parameters here of differential equations. You see, you will have this kind of the differential equations now, time dependent, because of course this happens during the irradiation. And then at the end, you come out, interestingly enough, you will see that these parameters, if you are in the low dose, high dose rate approximation, less than 10 gray, you actually come out with a linear quadratic equation. But the meaning of the alpha and beta now are related to the kinetic coefficients, so to the probabilities of inducing lethal lesions or potentially lethal lesions. So they have now a meaning, a more molecular meaning, and also now they are time dependent, which is something which is not in the classical microdosimetry. I mean, it is implicitly in the microdosimetry model, because beta, of course, is time dependent, but it's not explicit. Here you have an explicit way to give the time dependence of the beta parameter. Now, there is another model that I want to show you, because this used to be very popular. This is also from the 80s. It's very popular for its simplicity. And there is a book also here. I also have this book, even though we will see that one day I should put it in the trash, but for historical reasons I keep it. It's a model due to Chadwick and Linhaus, known as molecular model. This model had the ambition to go beyond the multi-target model and the linear quadratic model, and even the LPL model in Berkeley, saying, okay, we really want to give a molecular explanation of cell death. So we do the model starting from the initial steps. What is the idea? The DNA is the critical module, and double-stranded break is the critical damage, period. Radiation causes double-stranded breaks, and this we know. And now there are two modes of inducing double-stranded break. One is in one radiation event, intra-track if you want, which is linear with those. And the other one is an interaction of two single-stranded breaks, which is quadratic with those. Then, of course, you can repair the DNA damage. But these are the assumptions. And you probably already see that these assumptions are wrong. These assumptions are wrong, and I will show you why. The result of this assumption is a very sophisticated equation. Of course, eventually being intra-track, inter-track, the final result will be a linear quadratic equation. But the meaning of alpha and beta is very complex and it's very molecular. You know, you see, this is the fraction of DSB not repaired, so they include the repair now. The probability of DSB according to direct double-strand break and so on and so forth, the proportion of those inactivating via direct SSB. It's all number of molecular parameters. So alpha and beta now have a complicated molecular structure. But essentially, the model of Chadwick and Linhaus is here. This is a picture from their own book. So you can have, the survival curve is linear quadratic because you can have a double-stranded breaks either directly intra-track or indirectly inter-track. But this is wrong, because if this was true, the dose response curve for the induction of DNA double-stranded break should be linear quadratic, and it's not. You see, this is an last time I showed you the data from the University of Darmstadt, from our university, from Markus Lobrich in biology. These are data even more recent, and this is a large collection of data on radiation-induced foci, gamma H2AX, in many individuals. This is blood from many individuals, irradiated at very low doses. So you see, it's not only that it's linear, you know, when you go at high doses, I mean, then it tends to be linear, but when you go to very low doses, down to very low doses, it's clearly linear. There is no reason to believe that these are many different donors. There's no reason to believe that it's not linear. And as a matter of fact, also all Monte Carlo simulation shows that this way to induce a double-stranded break is almost impossible unless you go to 500 gray, to enormous doses. So the probability that two independent electrons end up at 2 nanometers time 15 base pairs, you know, in let's say 2 nanometers time 3 or 4 nanometers is so low unless you have a huge dose. So this model is essentially wrong. We know now that it's not only that the interaction distance to explain the intra-track and inter-track is not at the nanometer level, but is at the micrometer level. That is what gives you the idea of the interaction distance. So for example, the formation of chromosomal aberrations. And moreover, it's not the double-strand break per se to be the critical lesion, but it's the clustered damage, the complexity of the DNA double-strand break that plays the role. So that is wrong, but I wanted to give you an idea, let's say, of how science evolved, you know, and then the wrong hypotheses are thrown away. Another approach is the so-called saturable repair model. This comes from Goodhead in 1985. The idea here is this one. You see, in all the models we have seen so far, we start from the assumption that we have one-track lesions, intra-track lesions, that will result, this is the alpha D, the initial slope. You know that in the multi-track model, this will be 0. In the alpha D plus beta D squared, this is the alpha. So the initial slope, you see that is the intra-track. And then because of the inter-track events, so when you go to high doses, you start to see a curvature here. Now you can instead assume that the question is different. I mean, you can have initial one-track lesions, but then you can have repair. So these are repaired. But when the repair is saturated, when you go to high dose, so when you essentially your repair machinery is not able to cope anymore with lesions, so when you are exhausting the repair enzymes that we have seen in the previous lecture, then this will go down and will become linear again, as indeed happens in the multi-track, in the multi-target single hit model. And as we have seen, there is a limitation of the alpha-beta model, because in the alpha-beta model, there is not the linear behavior. So it's an interesting hypothesis. Eventually, you see, the number of lesions, the number of lethal lesions is given by this equation, where you see T is the time, C is the number of repair enzymes. This is the new, if you want. So now we have another parameter here, is that how many repair enzymes you have to do this repair. So that's also an interesting approach. And there are many others. I apologize, maybe this is not very clear. You can probably find the original publication here. This shows many different models. You see, this is the target theory, single hit. This is the target theory multi-target, you see, with curvature. This is the LPL model. This is the RMR, which is very similar to the LPL. Saturation model by Goodhead. The linear quadratic model. This is the microdosimetry model, let's say, Keller and Rossi. And this is a modified linear quadratic model with hypersensitivity at low doses that I didn't discuss here, but there are then even other models. This is a nice review of many models of radiation action. If you don't find it, let me know. I will give it. In the final part of this lecture, we will now focus on the high LET radiation and the heavy ion.